Okay, so good afternoon, everybody. Welcome to the colloquium of UFABC. Here, today we'll have Diego Restrepo from University of Antioquia, Medellin, Colombia. I couldn't find his whole CV, so I just have some brief info here. So I think he did his master's in the University of Antioquia in '97, I think. He went to do his PhD in the University of Valencia, and he finished at I think in 2001. And since 2002, he's a professor in the University of Antioquia, and he did some postdocs along the way, and he will talk to us about the things that he's working on currently. Right. So please, Diego, and thanks for accepting the invitation. And maybe so one more thing. Maybe it's best if your camera is off, and then in the questions you can turn off.
Camera.
Okay, sorry. So yeah, microphone, yes. And then the next one, yes, that's right.
Okay. So let us start. I will talk about a model that we are working on that is related to the three phenomenological problems of the standard model. The small length of neutrino masses solved through Dirac neutrinos, baryogenesis, and dark matter. So this work is done in collaboration with Andrés Rivera of Universidad Antioquia, my institution, and Walter Tangarife. In this moment, I am here in Unicampi, working with the phenomenological group from here in related topics. So I will start with the first problem, related with electroweak baryogenesis. That is the problems of the asymmetry between matter and antimatter in the early universe. This problem is still open, and in particular, we already know that we cannot solve this problem with only the standard model, because in the standard model we have all the ingredients, but the phase transition is not strong enough. To have one strong transition, we will require a Higgs mass of around 40 GeV, that is obviously in contradiction with the real one. So the standard model cannot be used to implement baryogenesis. There is still problems also with theories beyond the standard model because of the required source or CP violation. These sources of CP violation that have some contamination from standard model fields. For example, if the complex Yukawa have some standard model field, or even if one exotic field has some charge under the standard model, like a doublet, this in general imply very large values of the electric dipole moments that in general are in contradiction with the experimental measurements. So, in particular, for example, the two-Higgs doublet model and supersymmetry are very constrained because this problem basically are ruled out also as explanation of baryogenesis. So the people have started to think about what are the minimal ingredients to have successful baryogenesis at the electroweak scale, beyond leptogenesis. So the idea is to attack the two problems. One, to have a more strong phase transition and have additional sources of CP violation that are free from this constraint from electric dipole moments. So the first difficulty can be solved, for example, if we add one standard model scalar singlet that is inner under the standard model. The inner feature means that at zero temperature, this scalar singlet doesn't develop a vacuum expectation value. However, in order to study baryogenesis, we need to make them set up at some temperature, and maybe there in the effective potential at that temperature, this scalar singlet can really acquire some vacuum expectation value. And if this happens, if this condition can be met, this implies that the electroweak phase transition can be made more strong, even first order. So this is already studied and works. So if you include one standard model singlet that develops a bed at some temperature, this can be used to have a sufficiently strong electroweak phase transition. Note that this scalar field needs to be singlet under the standard model gauge group. And the same is basically what we accomplished for the CP violation terms. The idea here is to have some coupling, for example, a Yukawa coupling involving only a standard model singlet with respect to the gauge group of the standard model. For example, a Yukawa involving the previous singlet scalar and a singlet Dirac fermion. If this Yukawa is complex, this can be easy to accommodate against the result from electric dipole moment, can evade these constraints, and can be used as the required source of CP violation. So these two ingredients have been recently well developed, and there is one, let's say, self-consistent setup to have electroweak baryogenesis at the electroweak scale. This is basically made through U1 gauge lepton numbers or gauge baryon number symmetries with one anomalous Z prime. The role of this C prime is transferred the CP generated by this complex Yukawa to the standard model sector. This is physical review letters of some years ago, but Carena and collaborators. The idea of having this simple abelian station is to avoid the constraint from the LAC and open the possibility to have a node Z prime. Here, for example, is the constraints in the typical abelian group U1B-L. And we can see here that the constraints from the LAC are all this yellow area that exclude a small value of Z prime for a wide range of G prime couplings. So the idea then is to make the abelian station in a such way that these limits can be avoided. For example, obviously, if you implement a U1L symmetry, then the Z prime cannot be longer coupled to quartz, so cannot be produced directly at the LAC. So automatically, these limits are evaded. On the other hand, if you have, for example, baryon number gauge baryon number symmetry, so the Z prime can couple to leptons. So this is still produced at the LHC, but the signal, the main signal is to digits, and the constraints from digit are much lesser than the ones coming from the leptons. So again, these windows open in this kind of model. So the idea to consider these possibilities is to allow the Z prime to be light enough. And in this way, we can easy the transferring of the ZP violation to the standard model sector. I mentioned before that the Z prime need to be anomalous at the at the scale of the standard model Higgs, but the model is still anomaly free at some higher scale. Let's say the 1 TeV scale, where the other fields required to cancel out the anomalies are present. So, for example, it is well known that to cancel abelian anomalies, you need extra singlet fermion. So the idea here is to have this fermion related directly to the symmetry, acquiring the masses through the Baryon expectation value that break the symmetry, and to put this Baryon expectation value very high, let's say at this 1 TeV scale. In that case, at the moment of the electroweak phase transition at the standard model scale, these heavy fields are already decoupled. So the Z prime is in some sense anomalous at this standard model scale. So it is one important ingredient to this mechanism to work. So we require this kind of anomalous particles, the heavy ones that are associated to the cancellation of the anomalies. And these anomalies can play the role perfectly of the dark matter fermion particles that can couple to the scalar singlet to have the CP violation phase. So in some sense, everything is self-consistent. In the formulation of these anomaly-free models with anomaly cancellation, the more straightforward way is having Dirac neutrinos. So in this model, again by Karen and this physical review letter, they had in particular either one lepton or baryon gauge symmetry. Each one of these symmetry have Dirac neutrinos and some set of heavy fermion that play the role of the dark matter. So this was, let's say, one specific model to accomplish the idea, but is not a model that can really explain all the required phenomenology related with the problems of the standard model. In particular, the explanation of the neutrino masses is not there. And the neutrinos are pure Dirac, acquiring masses like the other fermions. So there is no explanation for the smallness of the neutrinos. So in this work, we want to make a more systematic study about the possibilities to have a self-consistent model, including also one explanation for the smallness of neutrinos. For that, we use two other well-known ingredients. One of them is a method to find anomaly-free theories. These methods basically implement the possibility to find solution to these Diophantine equations in a systematic way. And once you are able to implement this methodology, you end up with a great pool of possibilities to explore the phenomenology of specific realizations. So the methodology that I will explain later is based also in one physical regulator by Costa and collaborator. At that moment, Costa was one master student in USP, and he's now working in the doctoral degree at Fermilab in related topics. So this is also one important result that can be used to systematically try to extend this problem. And to explain also neutrino masses related with dark matter, we have this idea of scotogenic neutrino masses, where the generation of the smallness of neutrinos is related to heavy particles that are in the dark sector of some theory. For example, the dark sector associated to these abelian symmetries. See, the idea of the scotogenic neutrino masses is rather old now. Is this paper by Ma that he tried to publish as PRL, but finally appear as a normal PRD, but is the most important paper of Ernest Ma until now. So the idea is to combine the possible solutions to the anomaly cancellation and to figure out the required fields and specify of which of them will be used as Dirac neutrinos, and with other fields will be just anomalons that can be used in the dark sector to explain the dark matter problem. So in the work that we are concentrating now, we are trying to make a systematic study to check possible models around this full idea. So the new contribution is basically to have, in addition, a consistent setup for neutrino masses. So the idea then is to solve off the phenomenological problems of the standard model with a dark sector. And in principle, this dark sector is quite arbitrary in addition to the sector in which the known particles lives. We add one, let's say, orthogonal sector that is separated from the standard model, and that can have a complete set of new particles. These particles in the dark sector can communicate with the standard model through some portals. For example, we are interested here, for obvious reason, in the Z prime portal. So we are working with anomaly-free abelian symmetries in general that are associated to a new force, let's say a bit force. In addition to the photons, we have this another abelian new interaction associated with the Z prime, and usually to have really one anomaly-free theory, you need to compensate the lack of chirality of the standard model with extra fermion content, typically in the form of additional fermion singlets, doublets, and charge singlets. Here, for simplicity, I only focus in the standard model singlet fermions. So, for example, in that case, typically to solve the anomalies, we require a set of new singlet Dirac fermions, from which, in general, you can generate Yukawa couplings with some scalar field. So the idea is that this scalar field will be the same scalar that breaks down the abelian symmetry, like in the standard model. You use the Higgs not only to break the symmetry, but also to give mass to the fermions. So this phi here is also related to the spontaneous symmetry breaking of the abelian symmetry. So when this field acquires the background expectation value, we have a mass for the fermions. So the anomaly, the model is anomaly free at this scale. Let's say this 1 TeV scale. but very well below this scale, let's say at the scale of the standard model, these are the particles that I was talking before as anomalous. Because at this level, the theory, after the spontaneous symmetry breaking of the U1, looks as if the currents were anomalous. And this is important to have the proper transference of the CP violation in the dark sector to the standard model 1. So as I mentioned before, in order to have the Z prime sufficiently low, we require these symmetries to be very specific to avoid the constraint from the LHC. For example, if this is one gauge baryon symmetry, we can still produce the Z prime, but the Z prime is no longer allowed to decay into the lepton, but only into jets, and the constraints here are lesser. On the other hand, if we choose the gauge symmetry to be electronic one, gauge lepton number symmetry, in that case, the production is completely killed and the signal from the LHC disappears. Especially if the chart of the standard model is 0. Okay, so we are interested in these two types of symmetries. As I mentioned before, the set of fermions can obtain chiral masses and form a massive Dirac or Majorana singlet fermion that can be used as dark matter candidates. So, for example, I have here this Dirac fermion composed from this set of chiral fermions that are required to cancel out the anomalies. I use here the case of 2, but in general we can have many. Typically one certain number n that in general is larger than 4 to really have no trivial anomaly cancellations. Because, for example, the normal cancellation one, the U1B minus L, that is the chart assignment -1, -1, and +1, these only have right-handed neutrinos with 3-level neutrino masses. And in that case, the model is anomalous, is anomaly-free at the electroweak scale. And the mechanism to transfer the CP asymmetry doesn't work. So you need to have a sufficiently high number of fermions and give them high masses in order to everything to be self-consistent. So in general, we expect that the systematic study of the model gives to rise the possibility of multi-component dark matter. So in addition to the singlet scalar that breaks the symmetry, we require another inner scalar that doesn't develop even at 0 temperature, but that can couple to the dark matter candidate, for example, through a complex Yukawa coupling. This complex Yukawa coupling is the source of the CP violation required by the conditions associated to baryogenesis. In order to this Yukawa to really work at the source of the CP violation, these singlet scalar need to be the same that the one that is participating in the electroweak symmetry breaking by making the phase transition stronger. So this is the singlet scalar that play the two roles. For one side, increase the phase transition, make the transition stronger, altering the wall of the bubbles, and in the other hand, allows the possibility to have this Yukawa sector complex in the dark sector. So in this way, we can avoid, because all these are singlet under the standard model, we can avoid the strong limits from electric dipole moments. So this is basically the setup. And in our work, we want to include also the possibility to have proper neutrino masses and very specific models. So in summary, we have the standard model here are written in one convention in which only the right part of the fields are explicitly shown in the table. So this is the conjugate of the left-handed doublet is the right-handed one. We have the other right-handed fermions. In addition, we have the Higgs doublet that in this setup, we will see that is neutral. This is the standard model content, and we want to extend this with either one baryon gauge symmetry or a lepton gauge symmetry. For that, it is well known that in addition to some set of singlet standard model fields, we need also a set of lepton doublets. In the limit that these two charges, minus S prime and X double prime, are equal, these two doublets becomes vector-like. And the same happens with these charge isosinglets. In the limit that these charges are equal, these two particles are also vector-like. So in general, in order to have this symmetry, we need this kind of doublets and isosinglet to be with arbitrary charges that avoid them to be vector-like. And finally, we require the singlet scalar field that break down the symmetry and give mass to all the heavy fermions. And in addition, the singlet scalar that is required to have successful baryogenesis. In particular, we can have here a very large set of singlet fermions, depending on the specific solution. And here, in general, include the three generations. Sorry. Obviously, in the baryon, the gauge baryon number symmetry implies that the charge of the lepton doublet and the electron is 0, and vice versa. The lepton symmetry implies that the charge of the quartz is 0. From this, let me show the main result here. We end up with this condition on the specific charge of the quartz that can be summarized in this expression here. So we have that, in fact, after all the anomaly conditions as imposed, we end up with the condition that the quartz charges, this implies according to the table, the value of the quartz charges are are the same in absolute values, and also the lepton charges are the same in absolute values, and the Q charge is related to the lepton doublet 1 through this relation. So what this relation implies? First of all, if the doublet that we introduce are vector-like, this implies that S prime is equal to S double prime. So in that case, you in general have one L different from 0 if you want to have Q different from 0. So without these extra non-trivial standard model fields, always you have a abelian symmetry that have both sector charges, not only the quartz but the leptons. So if you have only to have charges in the quartz sector, in principle, the only requirement is to put this free parameter that is correspond to the lepton doublet charge to 0. So you put this here 0, and you have a self-consistent baryon number, provided that these extra fermions are no vector lie. In that sense, the baryon number symmetry is quite automatic. You always can have it. So the idea is that we use this paper that I showed before to find all possible solutions involving from 5 to 12 integers. So we have solution, let's say, with a set of 6 integers and another set with 12 integers. With the implementation of this methodology, we end up with around 400,000 solutions of integers satisfying these two conditions that are important to anomaly cancellation. From there, we need to filter that ones that we require to satisfy effective neutrino masses. This condition reduce this 400 solution to only 1,000. So in this 1,000, we can use the simple one just to illustrate a simple solution. And this is the one that I will show in this table here. So the solution itself is basically this one is 1, this one here, 1, minus 6, 5, minus 2, and minus 3. You can see here that if you sum this 10 minus 5 and 5, you have 0. And also, if you make the cubism of these numbers, 1 to the cube, 5 to the cube, 5 to the cube, minus 2 to the cube, and minus 3 to the cube, you also have 0. So this is the basic condition for anomaly cancellation. In addition, x prime is different to x double prime, so you avoid the vector lies. And from the formula, you can easily get the charges for the quarks. And there is no place for lepton number here, so the leptons are automatically 0. So it is a self-consistent baryon number solution built from one Diophantine solution with only, we can count 1, 2, 3, 4, 5, 6 integers, with 6 integers. Remember that with initial setup of a successful 1,000 solution have integer between 5 and 12. This is one example with 6. So, in order to have effective neutrino masses, we require in this set that we have two repeated integers, 5 and 5. And these are associated to the charges of the right-handed neutrinos. Ideally, we will need 3 in order to have 3 massive neutrinos, but we know that to explain the neutrino phenomenology, we can also have a consistent explanation with one of the eigenvalues massless. So this setup with only 2 right-handed neutrinos is consistent. With these 2 neutrinos, we can guarantee with this value 4, 5, minus 5, that the effective neutrino operator at dimension pi is allowed. So we guarantee that Dirac neutrino masses can be obtained under general circumstances. So this number here, this chart for phi here, guarantees the effective neutrino, Dirac neutrino mass appearance. Finally, once you solve the problems of the neutrinos, we need to check the self-consistence of the non-trivial field assignation. So here, we only need to check that the leptons, these extra exotic leptons, both doublet and singlet, acquired proper masses from the same spontaneous symmetry breaking, and this is automatic because know that 1 minus 6 is 5, so the leptons can couple to the singlet within masses, and this happen with the isosinglet charge scalar. So everything get masses and get the masses at the scale of the spontaneous symmetry breaking of the baryon symmetry. And after we have this self-consistent setup that guarantees the baryon number symmetry, we still have, let's say, three integers to be used. And are these two charges, -2 and -3. So these are assigned to two chiral fields. These chiral fields then can acquire a Dirac mass by coupling to the singlet fermion. So this can be a good dark matter candidate that is a singlet neutral Dirac fermion. So this is the dark matter candidate. And with this, we also need to guarantee the complex coupling to have CP violation. This is done just by assigning the charge -5 to the inner singlet. So with this assignment, we guarantee both the sufficiently strong electroweak phase transition and the generation of the CP violation. Because this Z prime is clearly anomalous at the standard model scale, this asymmetry can be transferred automatically to the standard model particles, and everything is self-consistent at this level. The one thing missing is the realization of the effective Dirac neutrino operator. This is, let's say, always guaranteed because there are always a standard model extension, or let's say these abelian stations that only involves scalars that can generate Dirac neutrino masses. This extension with only scalar doesn't affect the anomaly cancellation condition, so you can always, without any restriction, can add these extra scalars and have the realization of the effective neutrino mass operator. In particular, this is done with a set of 4 isosinglet charge scalars. We need 4 to have masses for 2 generations of neutrinos. So this is our extra 4 complex degrees of freedoms. And with this charge singlet, we can have this scotogenic contribution where the heavy particles in the loop belongs to the dark sector, and the one loop is automatically generated because we have chosen the proper charges for these extra isosinglet particles. So this is the realization of the Dirac neutrino mass operator through this mechanism that is known as the Darcy model. That is a generalization of the Dirac model with the standard model fields, because in the not dark case, this can be the usual lepton doublet and this can be the usual right-handed electrons. And this generate also neutrino masses. This is the Dirac mechanism, but it's not related at all with the dark sector. Here, we are, let's say, scotogenizing this mechanism by changing the leptons for the standard model lepton for some exotic one, and the same for the isosinglet. So this is the well-known Dirac Darcy model. So we have everything: neutrino masses, baryogenesis, dark matter, and our final result. Let me show the final result here after Dirac detection is in this plot, where we have a similar plot that I showed previously, but now with the full window open. We have the gauge coupling of the baryon symmetry, the set prime mass, starting from 10 to minus 1 GeV more or less. We have a lot of points satisfying the proper relative abundance and the Dirac adaptation. These are the blue points. And in addition, we need to check that the right baryon asymmetry is generated. This work is still in progress, but we have already some points that satisfy everything. There is some constraint that we need to take into account here. There is the lesser constraint from the lepton, from the LHC in the baryon number case, another constraint from flavor physics, and maybe the most important one comes from the right-handed neutrinos. The right-handed neutrinos are relativistic and can affect the early cosmology, and particularly changing the effective numbers of relativistic degrees of freedom in the early universe. This imposes some strong constraint in the vacuum expectation value, but elsewhere we still have some windows that is still open and can be explored with future experiments improving this observable. I want to end up with this plot that is our result, and from here to conclude that in fact we have like 1,000 self-consistent possibilities to explain dark matter, proper electroweak baryogenesis, and Dirac neutrino masses, with the explanation of why the neutrinos masses are small. From these 1,000 possibilities, we choose the simple one just as an illustration, but because all the 1,000 possibilities are anomaly-free models, all of them deserve to be studied, and some of them are very interesting because they involve, in general, multi-component dark matter with multi-generational also dark sector families. So now I finish here. Thank you.
Thanks, Diego. So I think, yeah, you can turn on your camera, and we have time for questions. Questions and comments. Okay, so I have one. So let me see if I understood. Yeah. So your baryogenesis scale is at the electroweak scale, is that right?
Yes, electroweak scale. It's
okay.
The neutral one.
And they are mediated by which fields, for example, in your simplest model, for example?
Yes, the phase transition is made stronger by this singlet scalar. And the scalar that I call X. This one from here. The singlet scalar. And the CP violation is the coupling between the dark matter particles with that singlet scalar. That Yukawa coupling is the sort of the CP violation. And the messenger, the transfer of the chiral asymmetry to the standard model is the anomalous set prime. These are basically the three ingredients: the improving in the phase transition, the CP violating coupling, and the transfer to the standard model asymmetry.
Okay, I see. Yeah, okay, interesting. Yeah. So more questions, especially from the students, maybe. You can use the chat or open your microphone and make questions. Okay, so I don't see any question right now. So let us thank Diego again. So thanks, Diego, for the presentation. Next week we won't have this colloquium, and then we will come back in 2 weeks' time. So thanks everyone for attending and for your attention. See you in 2 weeks.
Goodbye.
Thanks, Diego.